Welcome back to Boson Buzz, where we unpack the tools that are reshaping our world. I'm Monty Molecule. Today, we're talking about getting lost, not in a forest, but in a place where all our usual guides fail, deep under the ocean, inside a mountain, or in the concrete canyons of a big city. Our brilliant GPS satellites can't see us there. Our magnetic compasses go haywire. We are, quite literally, in the dark. For a long time, that meant being blind. But what if you had a compass that didn't need the stars or magnets? What if you had a guide that could feel the invisible shape of the world itself, the gentle tug of gravity, the hidden density of rock? That isn't magic. It's the next frontier of navigation. Meet the explorer that never gets lost, the quantum gypsy. Our story starts with a problem you can feel. Imagine you're the pilot of a giant submarine, tasked with mapping the unexplored seafloor under the Arctic ice. It's pitch black. Your GPS is useless. The signals can't reach you through water and ice. Your inertial navigation system, which tries to track every turn and acceleration, has slowly drifted. You're not sure exactly where you are, and worse, you don't know what's below you. Is it a safe, muddy plain, or a jagged underwater mountain peak waiting to tear into your hull? You are navigating a closet while wearing a blindfold, and the furniture keeps moving. For centuries, our main tool for this has been the humble compass. It points north because the Earth is a giant magnet, but get near a chunk of iron ore or the steel hull of a ship, and it lies to you. We needed something better, something that could sense a truth that never changes, no matter where you are. Scientists found that truth in the most unexpected place, not in magnetism, but in gravity. Here's the simple, powerful idea. The Earth's gravity isn't the same everywhere. If you're standing over a dense bed of iron ore, the pull is a tiny, tiny bit stronger. If you're floating over an underground cavern, the pull is a tiny, tiny bit weaker. These differences are incredibly small. Feeling them is like trying to feel the weight of a single grain of sand added to a loaded dump truck. Our bodies can't do it. Normal machines can't do it. But a new kind of sensor can. It doesn't measure gravity with springs or weights. It measures gravity with nothing. Or more precisely, with the ghostly behavior of atoms. It sounds unconventional, I know, measuring gravity with atoms. But stay with me, because the analogy is elegant. Think of this sensor not as a scale, but as a highly precise and sensitive plumb bob that weighted string builders use to find a true vertical line. But instead of a string, it uses the wave nature of atoms themselves. It's not checking which way is down, it's measuring how strongly down is pulling, with remarkable accuracy. This is the heart of the quantum gypsy, a device called an atom interferometer. Let's break down that scary name with a simple picture. Imagine you have a single atom. Now, thanks to quantum physics, this atom can behave not just as a particle, but also as a wave, a fuzzy cloud of possibility. Step 1. Scientists trap a cloud of atoms and cool them down to just a whisper above absolute zero. This makes them incredibly still and calm. Then, they use precise laser pulses to split this atomic cloud. Not with a knife, but with light. It's as if you take that fuzzy cloud and gently tease it into two identical copies, sending them on slightly different paths, one ever so slightly higher than the other. For a fraction of a second, these two atomic clouds fall. The lower one is just a tiny bit closer to the Earth. And because gravity's pull gets stronger the closer you are, that lower cloud feels just a slightly stronger tug. This minute difference changes the tick of its internal quantum clock compared to the higher cloud. After they've fallen, another set of laser pulses brings the two clouds back together and merges them. This is the moment of truth. When the two atomic clouds reunite, they create an interference pattern, like the ripples from two stones thrown in a pond meeting each other. If the ripples line up perfectly, it's one signal. If they are out of sync, it's a different signal. And what determines if they're in sync? The subtle difference in gravity's pull they each experienced. By reading this atomic ripple pattern, the sensor can measure the strength of gravity at that exact spot with staggering precision. So, back to our lost submarine. It wouldn't just have a compass. It would have a quantum gypsy on board, a box that constantly, silently drops and catches atoms. As the sub moves, this sensor feels the invisible gravity landscape below. Passing over a dense underwater volcano creates a tiny gravity hill. Passing over a deep trench creates a gravity valley. The submarine's computer compares this live gravity map to a stored map of the Earth's known gravity field, a map that is as unique as a fingerprint for every square kilometer of the planet. It's not looking for where it is under the sky, it's looking for where it is on the gravity map. Aha, the computer says. This precise pattern of little tugs and pulls matches this spot right here, 300 meters east of the underwater ridge. It has located itself, not with satellites, but by feeling the shape of the planet's mass beneath it. The blindfold is off. The applications explode from there. Imagine a truck with a quantum gypsy driving slowly over a city street. It's not taking pictures, it's taking a gravity scan. It can find forgotten pipes, sinkholes forming under the asphalt, or ancient buried foundations without digging a single hole. In mining, it can pinpoint ore deposits from above. In archaeology, it can map entire buried cities from a drone flying overhead. And it goes beyond Earth. On the Moon or Mars, where there's no magnetic field for a traditional compass and GPS doesn't exist, a quantum gypsy would be the perfect native guide. It could navigate by the gravity of the mountains and craters, allowing rovers to traverse with pinpoint accuracy, completely independently. This technology takes the most reliable force in the universe, gravity, and uses the strange rules of the quantum world to measure it. It turns the entire planet into a signpost, and every hidden structure into a readable marker. Its navigation returned to its most fundamental principle, feeling the lay of the land. But now we can feel it with the sensitivity of a cosmic whisper. From being lost in the dark to seeing with the hands of gravity. That's the quiet revolution of the quantum gypsy. It's a tool that doesn't look out to the stars for direction, but into the fundamental fabric of matter and space beneath our feet. It turns the whole world into a detailed map, written in a language of subtle pull that only atoms can read fluently. It reminds us that sometimes, to find our way, we don't need a better set of eyes on the heavens. We need a more sensitive set of feet on the ground. If the idea of a compass that reads the secrets of the rocks and tunnels below sparks your imagination, please help Boson Buzz on its own journey of discovery. Give us a like and subscribe for more adventures to the edge of the possible. I'm Monty Molecule. Until next time, have a safe and curious week.